Hello, good morning. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka. This is the lecture series of AS and A-level chemistry. Today is the 23rd lecture, and it is on reaction kinetics. We have been also discussing in the 22nd lecture the reaction kinetics. We talked about rate of reaction and what are the factors affecting rate of reactions. And at that stage, we finished our 22nd lecture. Now we come to the 23rd lecture. And what we are going to talk about, the methods to follow the course of a reaction, how we follow this method. The rate of reaction changes with time. That's what we discussed also. And we then select a suitable method to follow this rate of reaction. There are two main types of method. One is sampling, another is continuous method. What is sampling method? When we start a reaction, we take a sample at a certain time and then analyze this sample by chemical analysis. We can take an example. Here you see that hydrolysis of bromobutane. That is hydrolysis of bromobutane. We are hydrolyzing bromobutane and then we get the product. What we do, we removed a little bit of sample at a definite time and quenched it to stop or slow down the reaction. And then by cooling this sample in ice, the hydroxide ion concentration can be found by titration of the standard strong acid. This is a method which we call it sampling method. Another is continuous method. I show you an example of an instrument that is a digital colorimeter. With this reaction, the reaction with iodine with propane, we can follow the change in color of the reaction by this colorimeter, and thereby we find out the rate of reaction. Okay, and then we draw the graph and find out the rate of reactions. What is this one? The figure 1 is a volume of hydrogen gas in per cubic centimeter, and then time per second. We draw this and find out the rate of reaction. And then how we find out the reaction, the time and the product concentration in mole per dm cube. And then in this graph, we draw a tangent like this, And at that time, this is the time, and then rate at that time we can find out by how it is by AB by BC. If we take the SC and if we take the AB by AC gives us the rate of reaction at that time. Okay, then you see this figure C, formation of the time, some amount X mole. So let's say this mole of product has been formed starting with different concentration of the same reactant. That what we can also find out from this graph and this graph. Here is the formation of mole products, X mole product at the time Ta, and then formation of mole at a time B. This curve shows one type of rate of reaction. This curve shows another type of reaction, and we can do this. Okay, so this is what is called continuous method. Okay, then we take an example how to calculate the rate of reaction. What we are doing, we are taking example a cyclopropane, and then the product is cyclopropane and the product is propene. We follow this reaction at a definite temperature, and in this case it is 500 degrees Celsius. We measure the rate of reaction with time. Here, let's say this is what we have measured every 5 minutes, we measure the rate of reaction. What is it? Concentration of cyclopropane. And we also measure the concentration of propane. And this is your data. This data we get after each 5 minute interval. Okay, then what we do, we draw a curve on it and find it out. Okay, here is our curve. You see, this is propane. That's the product, concentration of product. And you know that each time the concentration of product increases. That's what we get from this graph or from the data we have been getting. Okay. And here, you see, here this is T1, and therefore with enlargement, we show this time in minute, and propane concentration with mole per dm cube. You know that this why we are calling it concentration, because we do represent concentration of any substance but in third bracket by showing the third substance. That what means this is the concentration of propane. This is the third bracket. And then, of course, you know that in a graph, we have to give the unit also. So concentration of propane, mole per dm cube, and the time in per minute. From here, then what we do, we find out the rate of concentration. How we do it? You know, you always know that delta is a sample. We show the difference between a substance, and then what we express in symbol by symbol delta in Greek or delta. So what is the that? Let's say we are taking time 5 minutes. So here is the 5 minutes, and then we get our concentration here. So concentration from 0 to difference in the concentration from 0 to 2.27 mole per dm cube. Okay. And then rate of concentration is equal to change in the concentration of the product divided by change in time. And then we get this. This is our this is the rate of reaction in this particular reaction. And in figure A, we showed it this like this, and figure B, what we said a few minutes ago, that it is an enlarged figure for a concentration up to 5 minutes. So we see that the rate of reaction changes with change in time for this reaction. Okay, then we go for a second figure, which is you show it here. How to draw a tangent and calculate the rate of particular points on a curve. We showed it earlier, and here we show the specific example. Let's say we want to find out the rate of reaction, and here in case of we are doing what we are doing, we are measuring the decrease in the reactant, that our reactant is cyclopropane. We measure the decrease in the reactant, concentration of reactant, and concentration unit is mole per dm cube, and it is and the time is per minute. So if we said take this point, we want to measure the decrease in concentration of this point. What we do then, we take the slope, and here you see that we have about 1.4 or so, but that is what 1.4. This is the extended of a tangent. This is 1.4, and so there is 35 minutes, and then the time in minutes is converted into seconds, and therefore we get 35 into 60, and then we get the concentration of reactant with time, and we know that concentration of reactant decreases with time, and concentration of product increases time. Okay, that's what I have discussed, and I showed the 4 steps how we do this, following rate of reaction or rate of decrease in concentration of reactant. Okay. Change in rate as the reaction product proceeds. How we can do it? As time passes, we know that the concentration of cyclopropane falls. We have seen it. We can find the rate of different concentration of cyclopropane by drawing tangential several points. So we did it, and now we are doing in several points. That means we take here the concentration of cyclopropane, the concentration here, and then it is 1.5 concentration, and then we do the concentration at 1.4. This is another is 1.4, and this is another is 1.0, and we can see that we draw this 3-point concentration. One is at time 0, and another is time at 10 minutes, another is time at 30 minutes or so. So 1.5 mole, that's the concentration, 1.5, 1.00, and then 0.05. That is what the concentration we are taking into consideration, and they take this data here, and then we can find out the decrease in rate of decrease in the reactant. No, here we have to note that the gradient, that is the rate in concentration, is constant. So that's what it is. Graph rate of reaction against concentration of cyclopropane shows that the rate is directly proportional to the concentration of cyclopropane. But if the concentration of cyclopropane is double, the rate reaction is double. If the concentration of cyclopropane falls by 1/3, the rate of reaction falls also by 1/3. Okay, that's what we see here, and we can calculate it like this. I show the table here, and then graph here, and show the data, summarized data. Now we go. What are the factors that affect reaction rate? General factors. The concentration is one of the factors. The concentration, higher the concentration of the reactant, faster the reaction. That's what we know. Surface area is another factors. It is breaking the solid into smaller pieces and increases the surface area. If the surface area increases, the reaction rate also increases. The speed of the reaction rate happening at the surface of solid. Effects also applies to reaction between liquids which do not mix. So we shake the liquid, if the reactant is liquid, and we shake it, and it disperses into a droplet, and thereby we increase the reaction rate. So surface area also. Another was what happened, that rising of temperature. That means with temperature, the reaction rate also increases. So there are 3 factors now we are talking about. One is concentration, another surface area of solids, another rising the temperature, and the 4th one is catalyst. I hope you understand what is catalyst. Catalyst is substance. It could be a solid, it could be liquid, it could be gaseous substance, and what it did, it speed up the rate of reactions, chemical reactions, without involving the substance in the reaction. And we need a very small amount of catalyst to increase the rate of reaction. And, there could be 2 types of catalyst. One is homogeneous catalyst, and another is heterogeneous catalyst. The homogeneous catalyst means the reactants, the phase of reactants and the phase of the substance are in same phase. Phase, we mean that if it is liquid, the reactants are in liquid, and the substance we take, which is also liquid, as a catalyst, then we call it homogeneous catalyst. But if the substance reactants are in different phase than that of catalyst, we call it heterogeneous catalyst. So this catalyst is very much needed for industrial purposes. So in most industrial processes involve processing a mixture of gases over a solid catalyst, most industrial is heterogeneous catalyst, and then we see that the rate of reaction depends on the concentration, surface area, temperature, and catalyst. We go to the collision theory. What is collision theory? According to collision theory, a reaction will speed up if the frequency of collisions, that means number of collisions per unit time, and usually the unit time we take is per second. That means number of collision per second which increases the reaction. The proportion of particles with energy greater than the activation energy will also increase the reaction. This is what is collision theory, and we use collision theory. Collision theory states that in order to react with each other, particles must collide in the correct orientation and with sufficient energy. So the particles might be atoms, ions, or molecules. When reactant particles collide, they may simply bounce off each other without changing. This is called an ineffective collision. Let's take this. We are taking hydrogen molecule and chlorine molecule, and then we're starting colliding, and this bouncing like this, and then there is no effective collision, or there is not sufficient energy. Therefore, we do not get any reaction, and this is called ineffective collision. Okay, then if the reactant particles do not have enough energy to react, they may change into product particles when they collide. This is called the effective collision or successful collision. That's what we showed schematically in this diagram. A, this is not an effective collision, you see, and B, this is an effective collision. It is an effective collision, and therefore we are forming hydrochloric acid by reacting hydrogen molecules and chlorine. This is our we will call this effective collision process. Now we talk about Maxwell-Boltzmann distribution. James Maxwell, a British scientist, and Ludwig Boltzmann, an Austrian scientist. These two physicists used the kinetic theory to explore the distribution of energy among the molecules in gases. They worked out proportion of molecules within a given energy at a particular temperature. Maxwell-Boltzmann distribution curve shows the distribution of energy for the molecules of gas under two sets of conditions. And that's what is shown in this figure. Maxwell-Boltzmann distribution helps to explain the effects of temperature changes and catalyst on the rates of reaction. That's what we have been talking. And this is what is the kinetic energy and the number of molecules with kinetic energy E. We draw the temperature at certain temperature. Here it is 300 Kelvin, and that is the 310 degree Kelvin. And we see the difference between the area and a total number of molecules involved in the rate of reactions. That's what we can explain with Maxwell-Boltzmann distribution curve. Well, that much we talked about the reaction rate or reaction kinetics, and that is the syllabus of AS level about reaction rates or chemical kinetics. But The next chapter is equilibrium. The next chapter in AS syllabus is reaction equilibrium. So we discuss this reaction equilibrium in the next class. Thank you for the attention, for your attention in the 23rd lecture of the AS level chemistry.